He knows, I know.
The food is for psychology's muckety mucks. You'll be gone just as the food's being served. Sorry.
Yeah, I didn't throw us all a party, I know.
You got Milky Ways. What are you complaining about?
Okay.
Might be better than what they're
A bag of Milky Ways is what I can afford. So, all right, hi everyone. We're going to continue on with galaxies, my favorite. And so, just a quick thing on grading. I am absolutely fine with anything handed in before April 22nd and or of the day of. There will be one of you who suddenly does all their homeworks and that's fine. Apparently you need a hard deadline. Or it could be that your semester didn't go completely as planned and you want to hand some stuff in late. That's fine too. Please keep this other thing in mind. Both me and my grader are in the midst of our end of the semester. He's also in classes. He's also doing finals and what have you. So between the two of us, we'll try to get that done. That's why I'm putting the end date on the April the 22nd, because then I can guarantee that I've got it graded before I have to have your final graded. Basically, they tell me when your final is, so they give us a slot. That means 48 hours after the date of the final, I have to have your final graded. I've run out of runway. I have no more wiggle room. I can't go, oh, I'll just grade all the homeworks that you just handed in together with your final. That just doesn't work. So I can guarantee that if you hand it in before April 22nd, that I can still grade it. That all okay with you? So late work, I know Blackboard now marks everything that you didn't exactly put in at the exact right time as late. Don't worry about it. You can hand whatever you want in, no questions asked, okay? Cool, all right. Yeah, that's just me grading. So we talked about what galaxies are made of, or at least the stars that we can see. So I showed you a whole bunch of pretty pictures, and I have more today. We noticed where the stars are being formed because they have those bright young stars. They don't live very long, so they must have formed just now. And I wanted to show you the winding problem, which is if you see a spiral arms like that, the problem is that it rotates a couple of times, and it basically, like the yogurt with the swirl in it, if you stir it 2 more times, everything is mixed together. So, and yet we see these spiral arms everywhere. So that's been called the winding problem, which means that the stars move at a different speed that the pattern of that spiral pattern moves. And the solution for that, I really, really hope that this video plays because it is hilarious. Thank you to the University of Nagoya in Japan. Please play. All right, let's see. Yeah, here we go. So clearly they got the whole department driving in a circle here, and note where, think here, this car brakes. We'll do it here too. Hang on for a minute. So essentially, as soon as somebody brakes, you kind of get a pileup. This is sort of what happens on the highway as well. You've seen this, right? Suddenly everybody in front of you is braking, and you go and you get there and go like, why was everybody braking? It's just somebody got spooked, slammed on the brakes, and then everybody sort of piles up behind them. So everybody has to slam on the brakes as well, and then we all speed back up. So you get a, like, let's see if they can find another one where, yeah, they pile, like here, they pile up. There's a bit of a pile up, so you get a dense, you get a knot of cars, but it's not the same cars, right? The cars in front then speed back up, and the front cars in the back sort of fill back into the, so you have a density. And so the pattern moves at a different speed than the individual cars do. Have you seen this? I've got this side nodding, so I'm going to talk to this side here, because I'm realizing that I'm standing over here, so I'm sorry about that. So, yeah, you've seen this, right? You drive at night, all of a sudden, brake lights, like what is happening, like especially when you go down a hill, for example. I've noticed that. So here, people go down a hill and suddenly see a whole bunch of traffic in front of them and go like, and hit the brakes, right? Some sort of panicky reaction. This is how you get traffic jams. And funny enough, those spiral structures, they're traffic jams. That's what they are. And so the individual stars go in and out. So these are all the orbits that were drawn like in the original 1980s paper when they figured this out. So the individual stars orbit in and orbit out, but the pattern is that spiral pattern that keeps going. And what we notice is that the spiral pattern trails, so if this is blue shifted, and so it trails the motion that we're tracking, right? So it rotates one direction, that the arms trail that motion. So that makes sense, right? So we've classified this, and not only that, we figured out why we get this spiraling pattern in the disk. I had to ask my colleague Karen Masters for her slides because she explains it so well. This is her jam, and so I thought it was really neat that yes, we have an explanation of why that looks like, why the spiral structure is there, but also why the structure seems to be moving at a different speed than the stars themselves. It's a traffic jam. Okay, so we also figured out that yes, all these classifications were originally from Hubble. All those lenticulars and especially the ellipticals are essentially just different viewing angles on the football. And so we have classes, and so we know what some of this morphology, some of the shapes mean, right? So this is another one where here's the ellipticals, and these are our digital pictures that we have now. As you can see, like you've got the big spiral structures, and you've got some of them with a bar in them, and then you've got the ellipticals over here. Now, that is something that you can classify. You look at it, and now you've seen this now a couple of times, you go like, yeah, I can tell you if that's an elliptical or if that's a spiral. And what we've noticed is that these are red and dead, so they're usually often clumped together, and they are red and dead, so they're not forming stars anymore. And these are blue, they're for star forming, they're not as massive, and they're typically not clumped together in clusters, they're more all around. So if I then put that data on it says large version on a cloud, this is the projector that we're going to use in a minute, sorry about that. And so we've got dimmer galaxies over here, bigger galaxies over there, bluer, color. Once again, I've stolen from a British person, and so color is spelled wrong. There's redder over here. So if you expect blue galaxies to be over here, they're a little smaller, they're a little dimmer, and they're all on the blue side, and they're all spiral. So this is what I'm expecting, and I now want you to notice something about, I am talking in very general terms. Yes, question, sorry.
Do you know what causes the bar?
We don't, which is awesome, right? It's a mystery. What we think is happening is there's a flyby, that can definitely cause a bar. Another thing that can happen is that the disk itself buckles and starts reorganizing itself. And it could have something to do with the dark matter as well. There's often more than one mechanism that you can have a bar, but it's very unclear how long they stick around. So you could be making of bars and breaking bars all the time, or as soon as a bar forms, it sticks around until the galaxy gets completely re-regulated. Now, another thing that I want you to note here is that I'm talking in these old declarative sentences, and you'll see, if you read a scientific article, you read a scientific journal article, or you read especially a press release or something that a journalist has written about science, you'll have these declarative sentences as well. But I'm talking about a population of things, many, many, many things, right? So if I say a declarative sentence like that, I mean this is true for 90% of them, 95% of them, 97% of them. Basically, your odds are pretty good that when you encounter a random one, this is what will happen. That doesn't mean that others don't exist, right? That's the exception that proves the rule, because what we had was like, well, we got red and bright, those are ellipticals, we got blue and slightly dimmer, and those are spirals. But, and we had some green galaxies in between, so I've studied that with some of my students. This is what it looks in real time, if you actually plot the real points. But then we had a really fun project since 2008, but this has been still going strong, And this is called the Galaxy Zoo. And this is where you'd ask everybody in the room, everybody online, which is the entire internet. Even in 2008, that was most people already. And so, hey, can you help us classify these things? We have so many of them. This is the brainchild of a graduate student who figured out that he was doing 50,000 of these a week, and if he kept doing it, he would never graduate. There was 250,000 to be done. So he asked essentially the internet to help him out. Let's see, like, is it a spiral? Is it elliptical? Can you click on the buttons for us? Can you help us out? Well, one of the things that happens is that, yes, the majority that we found here were spirals, and the majority that we found there were ellipticals. But we found some red spirals, and we found some blue ellipticals, right? There are exceptions to these rules, and if you start looking at everything, if you start looking at large numbers, you're going to get the rare stuff as well. Something like 8% of all spirals is actually reddish. We don't exactly know why. Maybe they stopped forming stars for now. There are a few galaxies that are elliptical that are in fact blue. They seem to be still forming stars. So those are interesting to study in themselves. I love the opening slide. I think that hasn't changed. Few have witnessed what you're about to see. Essentially, we've taken all this data. Please have a look at classifying. And say, like, is this an elliptical? So these were kind of buttons. If you kind of wonder, who has the time for this? Oh, wait. How does this work, right? So this is an incredibly old movie. I have even given up on finding a meme that actually connects with you all. I have no idea. Maybe two of you have an older brother or uncle that shows you to this. Who has heard of Monty Python at all? Right, okay, there's one very happy looking. All right, more people here than I expected. Great, awesome. Monty Python, The Life of Brian. There is this kind of memorable scene where he's talking to a crowd, right? And the whole crowd goes, you're all individual, and the crowd goes, yes, we're all individual. And there's one guy who says, no, I'm not, which is the whole joke, right? I've explained the joke so that it's funnier. Anyway, the point is, you ask a bunch of people what their consensus on a galaxy is. So classification by crowd consensus. The neat part is that the crowd works just as well as an expert on this, and in fact is a little more consistent. Because if you ask the same expert, right, guy like me, to classify galaxies, and then sneakily you give him older galaxies and you ask him to classify them again, but now on Thursday morning when he hasn't had his coffee versus Monday morning when I did, right, there's a difference. People are not that reliable. You may have noticed that yourself in your own life, right? So us as classifiers, we're a little subjective. But us as a group can be way more subjective. So this became a quite interesting experiment, and so we got a lot of classifications of, red spirals. This has spiral arms. It's just, they're not blue. This is an actual elliptical, right? So there are things like what causes these very differences and what can we get from these populations. There's another reason that this was very exciting. We have loads and loads of images, and we have loads of classification of what those things are. And you can imagine that if you are a person at, I don't know, Google who's trying to learn how to do classification of images, or we're trying to develop machine learning, this is a fantastic data set. Because no people are involved, so you can't accidentally, spill somebody's medical data on the internet or what have you. This is a well-described data set, and you're helping science, and in the meantime, you don't have to, you can try out your algorithms. And so we did have that question, it's like, how do we end up with ellipticals on one side and spirals on the other, and they have to go from one to the other somehow. So what causes that very different observational properties, right? We've got these disk things, these very thin disks that are clearly rotating, and then we have these blobs, these footballs that are, blobs. All the stars seem to be going in every which way. So what happened to this, right? So these were this next class, interacting galaxies, clearly two galaxies, but they're gravitationally interacting. They are exerting tidal forces. If you can remember back on week 2, when we were talking about gravity, tides were a big thing. Well, even on galactic scales, you can have tides. And so when you start seeing two galaxies together, you start seeing like they're getting a little bent out of shape if they get closer to each other, or really bent out of shape, right? So these two are two spiral galaxies, and this is a spiral arm that is basically losing, right? So it's completely rolled out and being tidally removed. You get something, I love the nickname for some of these, right? This is the Rose Galaxy. It's an astronomical picture of the day on, of course, February 14th. And so there's this, you know, these tidal arms seem to be coming loose as this nearby galaxy seems to be tugging on them, right? Tugging on them. And so these interacting galaxies, this is two still, but you can sort of see that they're starting to merge. And gosh, I don't know where one begins and the other ends. There's clearly a center here and a center here, but it's a bit of a train wreck. And this is the Penguin Galaxy. Again, found by all the volunteers looking at the Galaxy Zoo, because people started marking up like, we got this really weird looking galaxy. Is this normal? Should it look like that? Did your telescope break? You know, there's a whole chat group on this. And so you can sort of see the penguin here, but this one's being completely bent out of shape by its nearby little companion. And so this is the antenna up close, and it's two galaxies, but there's now bridges and everything has been rearranged. And there's, as a result, because the gas moves all over the place, lots of new stars being born. So these are often known as starbursts, something really hot and bothered, like it's going really fast in all its gas. Lots of different places where new stars are being formed, and so it's bursting in stars, right? So if I look at, this is the Hubble picture, if I then look at the photographic play from long ago, but you can see the tails, these tidal tails sticking out of this pair as well. And then you see something as strange as this, right? So there is a galaxy that looks sort of spirally, but it has a strange ring around it, but it also has these two other galaxies lurking nearby. This is behind it, this is actually in front of it. And we have something like this host object, which also looks like, yeah, there's a bulge, and then there's this clear ring and like nothing in between. So what we think has happened, and so if we want to figure out so we get these one, let's see, somewhere over here, we had the questions like, hey, is that the same galaxy? No, we get one snapshot at one angle, right? We get one camera angle during, it's sort of trying to piece together what's happened to this galaxy if you get one photo of the crash, right? From one random camera angle. So that's kind of tricky. So if you have something like this, you kind of go like, well, or especially this, you kind of go like, well, this has this one something to do with it. So you put what you think has happened in a computer and run the whole thing forward, right? So we can't wait until this happens, but we run the whole thing in a simulation. And so this is a simulated disk galaxy, and here's a smaller galaxy that instead of hitting the sides anywhere, we're hitting right in the center. So if you do a dead shot right through the center of this other galaxy, the shock wave essentially makes that ring, and then it sort of clears out most of the inner parts, so you only get a little bit of faint spirally structure left. And if I now look at it at the right angle, this is a slightly older simulation. All of you post-Shrek 4 people are not impressed with this anymore. I know, this is one of the first ones. This is very pre-Shrek 1, okay? So you should think of it as pre-Shrek 1, but it does kind of explain why we're still seeing a pretty decently coherent dwarf galaxy behind it, and why we see those rings and those spokes like it. Yeah, you can tell that this is a little older, but I like it that it shows why that curve looks like it does. And then if we look really deep, right, so this is where we take a really long exposure with a telescope, and you start seeing these fainter, fuzzy things. What you thought was a normal spiral, right? So we do this in nearby galaxies, so you can see like this is an overexposed star. You only see here's the background galaxy, but you also see that it has weird fuzz around it. And sometimes it's even clear. It's like looks like little rings or tails on either end, right? And is that the spiral structure? No, the spiral structure goes this way. This is sticking out on sort of an angle. And so what we think happened there, again, this is a slightly older simulation, but it doesn't matter because we've got a really big galaxy. The small galaxy sort of passes nearby, and then sort of gets stripped, again, through tidal forces into this longerish, taily thing. And especially sort of by the third passage is really a really faint arc of a galaxy. So maybe you're trying to find like whatever is left of the center. Everything else is smeared out over an enormous area. And so they're really hard to find. They're really low surface brightness. They're low brightness on the sky. But that is telling us that galaxies are interacting. They're gravitationally interacting. They hit each other. They're not island universes. The islands collide, right? And so when the islands collide, as the small island collides with a bigger galaxy, the small galaxy is sort of not in a good shape. By the end of it, it will be ripped apart into bits. We have a kind of brutal terms for these things. That's called galaxy cannibalism, right? As a big galaxy eating a small one. And so we can imagine that smaller galaxies don't survive the encounter, but what happens if two galaxies that are roughly the same size hit each other, right? So when these two, if they're sort of the same size, we get something like a close interaction. We get these tidal tails, lots of blue, more star formation than the two individually, and then during the merger, even a higher burst of star formation. So it's burning through most of its gas at a much higher rate, right? So instead of ticking along, getting a little new gas, making some new stars, and having like a blue disk, we're ending up with like all the gas either in the center or flung out. So whatever we do, we don't really have much gas at the end, and so we end up with, if we take two, here's a spiral galaxy. This is Shrek 2 level. So we have one spiral galaxy, another spiral galaxy. This happens to be our own Milky Way and Andromeda galaxy, and the two of them collide. They're about the same size. You see, lots of star formation happening. Look, they turn bluer for a moment, and they start tidally tossing stars and outer bits away. Little bursts of star formation happening, burning through all the remaining gas, and as it's colliding again, we saw that something basically collided here, like entered in the center, right? And then they collide again, even more star formation, dust that gets produced, and more star formation. All the orbits of all the stars get rearranged. They're not neatly arranged in going in circles anymore. They're going all over the place. So we end up, if we wait a little bit, with something that looks pretty round and looks like an elliptical. So it burns through all the gas, halts most of the star formation, and then you end up with rearranged orbits that look like a ball. This is how you make elliptical galaxies. Or lenticular, right, if you have a little bit of the dust left. Yeah. Thank you for the nodders. I know it's the end of the semester, but anybody who nods is really keeping me going here, all right? So, how long does it take for the Milky Way to rotate around once? Can you remember? 1 billion years, and 200 million years, a few tens of million years, or 65 million years? Can you remember roughly what that was? 1, 2, majority B. Okay, 200 million years, which is kind of neat. That means that, for example, when, well before what we think of as the dinosaurs, the earlier dinosaurs, we were essentially at the other side. So more than 65 million years ago, so 100 million years ago, when T-Rex was running around, we're on the other side of the Milky Way, which is a really strange thing to think, but yes, T-Rex saw the other side of the Milky Way. We didn't. And so how long, if you kind of saw that, right? Yes?
Horseshoe crabs have been around twice.
Yes, this is, I love this, right? So I will use that. I've seen them in Maryland. You see that coming out of on the shoreline, you go like, yep, that's a dinosaur. Blue blood, the whole thing, right? And so yes, horseshoe crabs have been around. Hey, it's a winning combination. It's still around, right? So you can sort of go like, certain species have been around the center of our Milky Way a couple of times. Considering how often a did you see how often each of these galaxies at least rotated at least once while the collision was happening? Okay, how long does this whole collision last at least? Volume in 1, volume in 2, and volume in 3. A, B, C, C, D. I got every answer, so okay, you know what to do. Turn to your neighbor, even if the two of you agree, and explain to them why you think this is the answer. Okay, so how often do you see either one of those galaxies rotate, right? Floating in 1, floating in 2, floating in 3. I got majority A, yes. At least 1 billion years. These things take a long time to collide. But on 13 billion years, that's only 10% of the time, right? So, and maybe some of them collide much faster. But the reason that we see them sort of mid-collision is because this is happening a fair amount, and it takes 1 billion years. It isn't over in like 10 million years or something like that. So we took, with the Hubble Space Telescope, a whole series of pictures of all these weird-looking galaxies, the ones that didn't quite fit in our classification. And so you see a bunch of them. Some of them are just close together. Some of them have these tidal tails. Some of them actually seem to connected already. This is a hot mess with, there's 2 cores, but everything else is mixed together already. And so this is sort of the galaxy's collision simulation. So we're taking 2 spiral galaxies. It is Shrek 2 level, sorry people, but the neat thing is we can swap back and forth to the, we're moving our camera angle and we're running time forward, right? And then we are just sort of fitting these Hubble pictures in there and running time forward, and at the same time you sort of see that the camera angle moves because we're seeing this pair from this angle. And then as we keep going, we're running time forward again. The two sort of separate for a minute. Yep, that looks sort of like this. Maybe the camera angle's a little off. And then keep going. And let's see what they look like as they, these last two, the last merger happens. Again, move the camera angle a little bit from this side. Yep, that's what this looks like. Right, so we saw a whole bunch that are at different times and from different camera angles. But they look exactly like what you'd expect if you put this in a simulation. If you put what we know galaxies are made of, dark matter, stars, gas, and then put it in a simulation where you put the rules in and say like, okay, if so much gas gets together, it becomes new stars. You put the gravity in, yes, we understand why these things look like they do, even though if you have a variety of shapes, right? So as I want to illustrate, like every time we get a better computer, people redo this because this is gas, and now for the first time I have a clock sitting there. So this is in mega years and millions of years. So the first interaction already takes something like 800 million years, but they've already shook each other up enough that both of them, you see the gas getting hotter, right? They color-coded how hot the gas was. Gets hotter and hotter, swarms all over the place, gets ejected as stars form. Oh, that was something that we hadn't looked at, right? We hadn't looked at where the gas goes. Well, if you get a collision like that, gas doesn't just fly by, they bump into each other. So it heats up, and the whole place heats up. Now, if I look at it in stars will just do a flyby, right? None of the stars hit each other. So that's where you get the tidal tails. This is what we see in the pictures. But the gas underneath is doing a whole different dance, where a lot of it either gets used in new star formation, or it gets head up so much that it doesn't cool down in star formation anymore, or gets ejected altogether. So it's a really great way of rearranging all the stars in 2 galaxies and using up all the gas, or at least getting rid of it. And so that tells us, yeah, that's how you get elliptical galaxies. You end up with like something like this. You go like, hey, do you see some of these shells? And yeah, we do. If we look deep enough, we see those around elliptical galaxies as well, that there is a little bit of that leftover stuff. And so you can sort of see the characters here. We've got gas, stars, we've got a face-on view, we've got an edge-on view. So different camera angles. You can imagine that anybody who makes these sort of sidles up to DreamWorks and goes, can I use your giant computer if you're not making Shrek 5 at the moment? And they do, right? They let us use these computers sometimes and render these simulations where we do put the physics in and then we run time forward. So it's now already 1 billion years, and the whole collision takes 2 billion years in order to complete. We think it actually took less time in the earlier universe. You see the gas blow up, and you see the stars rearrange themselves into an elliptical. I thought I'd make a progression of, improvement in simulations and not show you the Shrek one to start with, but they all seem to be in good agreement. So here's one where we now are looking at our Milky Way. We'll do this on the big screen in a minute. And again, you sort of see the counter, and where are you? The second galaxy is about to hit it. Right, there it is. The Andromeda galaxy. And there's a triangle in galaxy 733. This is our local group, and the Andromeda galaxy is moving towards the Milky Way. Here's the funny bit. For the longest time in this class, I got to say, we're about to hit each other, these two galaxies are about to collide. This is, I got to see the simulation. And this year a paper came out, it's like, yeah, we're not entirely sure that the Andromeda galaxy is going to hit us, because it might be coming straight at us, or it might give us a miss completely, right? It's actually very hard to see if something coming directly at you or mostly at you. So we haven't figured out the angle now. So again, hey, the thing that I was so certain of is being debated a little bit. But what I find neat is, like, we're going to end up in a elliptical galaxy in about 6 billion years. Our sky is going to look completely different. But 6 billion years, oh, that's also when the sun burns out. So, we'll have other problems as well. So you have ellipticals. Lenticulars are sort of leftovers, but what you can also imagine is that you have an elliptical, you accrete a new layer of gas, and then maybe you end up with a spiral. We haven't seen this. So there's only really one direction that galaxies evolve. They go from spirals. We see lots of spirals early on. We still see lots of spirals today, but we see an increase in number of ellipticals. So ellipticals are sort of the end state. And what you can also do is, like, why do we have such big elliptical galaxies? Well, if you merge two elliptical galaxies, they don't have any gas. All the stars are going whatever, every direction. So if you merge those two, you're just going to end up with a bigger blob. And so this is what we think is happening in clusters a lot, where smaller ellipticals basically merge with each other into becoming bigger and bigger elliptical galaxies. And sometimes you can still see the nucleus, the center of one of these, and the current record holder has 8 of those. So it's a merger of 8 elliptical galaxies. It's this massive thing. And so they're, okay, so I have a group work on morphology of the Hubble tuning fork. So this is how we classify things. Think of it as Hubble started this classification because he got all these photographic plates and he was trying to classify what he was seeing in order to make sense of it, right? And so you may get a hint from the fact that his ellipticals are on the left and his spirals are on the right. He thought the ellipticals was something that we started with, and then maybe end up with disks, right? He didn't know which direction the evolution was. And that was only something we figured out later. But we still use the tuning fork. Everybody knows what a tuning fork is. I don't know how many musicians I have in my room. I use that every day. But yeah, so this is like this sort of like chicken bone, wishbone. Yeah. I made plenty, so if you need a couple extras, that's fine. There was one time I ran out of them completely, and I never want to do that again, so I always make a little too many. Let me know if you got extras. And I've run out on this side. Let me get that right hand torque. Anybody got spares? Sorry. Thank you so much. Move that over to the side. One day I can walk and chew gum at the same time. At the moment, not so much. All right, any questions else about, galaxies? This is the stuff that I do for a living, so I'm absolutely happy to talk your ear off. I've got enough of them today. Maybe. Keep handing out pens and never seeing them again. Yes. I really want it back though. This is for me. Cincinnati weather. So we did hear about the supermassive black hole in the center of our galaxy. And then if we started looking at other galaxies, especially with radio, so for example, with this fantastic 1950s futuristic thing looking radio telescope in Britain. I love the fact that the hinges came from a battleship. You know, this is the kind of wonderful stories that you get out of the end of the British Empire. And so they were looking at these things that looked like radio stars, right? They were so small in the sky, but they were incredibly bright, and if they were really, really far away, and so with the Hubble Space Telescope, they took pictures of these things, and it's so bright that it's still making diffraction spikes. If you take that out, you're left with what does look like a galaxy, more like an elliptical galaxy. And so it's very unlikely that that was radiating all directions. But it was very, very bright, so if you have to have something, have to make something that bright, there's really only one thing. You take a black hole, a really big one, you have gas fall into it, and then you're looking straight down that jet. Right? That luminosity, that high brightness, that's what you saw if you're looking straight down the jet. This is the most efficient way to convert mass into energy. As this falls in, the mass gets converted into a very thin, very collimated, it's basically made into almost a jet, it is a jet of just a little bit of material and a lot of light going in that direction. And so 15 years ago, a quasar was observed that was found to be located 8 billion light years away. If our universe is approximately 13 billion years old, when did that quasar emit that light that we observed? 50 years ago, 5 billion years ago, 8 billion years ago, 15 billion years ago, 23 billion years ago. You see that quasar, and it's 8 billion light years away. When did it send out its light? 41, 42, 43. See, would you already see? Let's say 8 billion years ago. Yes, that's when the light left it, right? So these are, these black holes switched on a long time ago. In fact, with the James Webb Space Telescope, we've actually found these things almost 13 billion years ago. So we know that black holes have been around for a while. That is a bit of a challenge, because how do you make a million solar mass black hole right after the Big Bang? So it's exciting to figure out why. The sources that we found are called little red dots. And yes, there are little red dots in James Webb. And so there are these black holes that were essentially looking straight down the jet. The reason that you don't see the jet or you don't see the black hole much is because there's this torus, this donut of stuff around the black hole and the stuff that's falling in. And I noticed that you might notice here a couple of different very strange words around it, and I like this particular graphic much better. Again, what happened was camera angle, right? So if you're looking right down the jet, you're ending up with what's called a blazar or quasar, quasar stellar object, right? You're looking right down the jet. So that looks like some of these objects. But if I'm looking at it sideways, I don't see the jet directly, but I see the emission that comes off it from the side, and I'm seeing the donut and maybe the accretion disk. And if I'm looking completely on the side, I don't see any of the action right here, but I see a jet come out and I see maybe a hot torus. So all of these things were called different things, or QSO, another kind of QSO, quasars, BLAC, Seyfert. All these galaxies turned out to be the same kind of object, but looked at different angles. And whether or not the black hole was having gas fall in or not, when it was switched on or not. So switched on or not, and the rest was all viewing angle. And it took a while before we figured, because these are all different people that come up with different catalogs, right? They found things that are radio quiet, things that are radio loud, things that have X-rays coming out of them, some of them don't, right? So what is happening is it's all the same, and it turns out, yes, it all comes down to which angle you view it at, and whether or not it's switched on. But you do see something like this, and I want to reiterate this picture where you see the jet come out, you see it sort of hit the clouds much further away, and this jet comes from somewhere in the center, and we sort of followed that jet to its origin and took a picture of that black hole in M87. Right? That's a billion solar mass black hole. It's the biggest in the neighborhood, and the Event Horizon Telescope took a picture of this black hole and the one in our Milky Way, and that's sort of it. And they could do that. This one was 1,000 times further away than the center of the Milky Way, but it was also 1,000 times bigger. So it was about easy to see, or equally hard, I would say. And so you see these jets come out, like the galaxy's sitting here, but the jets are, the galaxy's about this size, and the rest is all this jet, right? These jets are almost the same scale as, or bigger than the galaxies they're sitting in. And so the black hole is in the size of, we saw that when we were working on the Milky Way, right? We saw that the black hole, the area of the black hole is almost the size of our solar system. It's tiny. It just got that billion or million solar mass black hole sitting in the center. And if it switches on, then it makes a jet that's bigger than the galaxy that it sits in. So it's influencing, if you have a black hole that size in the center and it's getting a supply of gas, it's shooting out jets like the other one is, you don't see this one because it's going away from us, but it's hitting the cloud over here. You get these jets happening everywhere, and this is the best picture of a nearby one. You see the optical, and this blue stuff is the radio, and the orangey stuff is the X-ray, if I remember correctly. And so you see the jet basically switch out on both sides, shoot out on both sides, and hitting all the gas around it. So that's the other way that galaxies can switch off. They grow a black hole in the center, and that black hole sends out two jets and heats out and ejects all the gas nearby. No new gas coming in, no new gas means no new stars. So that's the second way that we can switch off galaxies. This is the second way that you can have an elliptical galaxy switch off. So when you get a black hole and when it's active and when it isn't, it's really interesting. Our Milky Way's super not active. There's no big jet sticking out. All the gas can come in. We don't have something like this sticking out. We would see it. But many other galaxies do. So why are some active and some not? When did that black hole get there? And as far as we can tell, it got there really early, sometimes so early that we think the galaxy actually formed around it. So this is something that we're still trying to figure out. We have no idea. Right, so did the black hole form first? How do you grow these things? How are they so big? And so we think some of, this is an active debate that we're having, whether or not you need some of those mergers to make the black holes bigger. Some of it is like, yes, some people are saying, no, there's more than one way to do it. So that's something that I'm peripherally involved in. Hey, I said I like galaxies, right? Okay, here's the last 3 slides. The first one is, how often do you get to play with the Hubble Space Telescope? In my case, a little bit like 3 times over 2 decades. So these are my pictures, right? So these are the pictures that either I was involved with in the analysis, or they were completely set up by me and my group. So you have this particular background galaxies, and it's neatly highlighting this little spiral here. And you can see all the brown stuff there, right? So that's the dust, and that's what I study. You can kind of go like, well, if I see it over here, it must be over here, but there's no light coming from anything behind it, so I don't see it here. And so we use this as a backlight, as a sort of light table to see how much dust there is in the foreground galaxy. And if you wonder about all the stars here, we're actually seeing the whole thing through another nearby galaxy, right? This is in the outermost outskirts. These are all in a completely different galaxy altogether. This is Rubin's galaxy. This is actually something that I did while I was here at U of L. And so this is a galaxy 5 times the width of our Milky Way, about 10 times as heavy, and yet it looks like a neat little spiral. This has nothing to do with the galaxy. It is a foreground star from our Milky Way, and we ended up making this picture. It took about a year and a half to take each quadrant, because we had to take a section at a time, and then everything got put together in 2020. I got to present this picture as a NASA picture of the day, and all that good stuff. And then March happened, and I have no recollection of what happened after that. So, and then this is the last one. This is BV191, and this is a combination of both Hubble pictures and James Webb pictures. And so you can see the spiral, and you can see that all the dust here is neatly backlit by this elliptical galaxy that's further away. And so we took pictures with both Hubble and James graduate student, Clayton Robinson, is finishing his PhD working on that, seeing how the dust, the optical properties of the dust from that galaxy. So this is the kind of experiments that I'm doing. You have to have an accidental overlap of these two things, and I thought, hey, I get to show my three pretty pictures, right? These are my quote-unquote three pictures. So yes, we got a Hubble, two Hubble pictures and a Hubble plus James Webb picture, and two of them have been astronomical picture of the day, and that was on my bucket list. Like, I want to be astronomical picture of the day. It's one of the oldest websites on the internet. It started in 1995, if you believe it, and so the whole internet wasn't particularly big. Google may have started that year or the year after. And so it's a fantastic website because it's run by a couple of, I think, retired NASA engineers. They go like, I don't know how to do HTML code. It looks exactly like the clunky 1995. They have not changed the aesthetic at all, just out of sheer stubbornness. I can really appreciate it. But they have like a cool astronomical picture every day, astronomical picture of the day, and the two of mine got to be on there, which is like this. It got started when I got started in undergrad. So, okay, that was the things I wanted to show. We have, however, a neat bit to use the planetarium, so we'll switch over to that. Here we go.
That's your hint to get dark.
Yes.
So right now we're looking at the local group.
Andromeda, Large Magellanic Cloud, our Milky Way. Right, so I showed you a couple of these Shrek 2 level simulations. Of course, we keep redoing them because if we get a bigger computer, you can make them prettier. But the main thing's still true. This is pretty much what we think our spiral galaxy Milky Way looks like. We have a better idea now thanks to Gaia. We do know what Andromeda looks like, also thanks to the big Hubble projects on that galaxy. And so we know Andromeda is one of the few galaxies that's actually blue shifted, that's coming towards us. And let's see if,
There's going to be a crash of Andromeda.
Hey, okay, this galaxy looks familiar. That looks like the one that we crashed a small galaxy through, right? This is sort of at the same age, simulation, a little better. So, Shrek 2, I'm gonna go with. And so you see the collision, you see these tidal arms come out where stars form briefly, but then they fade because the bright stars die off, the blue bright stars die off early, and so then we are left with like a stream with just a few stars everywhere. So it's really, really faint. You have to have really sensitive cameras to actually pick that up. That was it already. Oh, so they already merged, right? So then, so if you wonder why we don't see those tidal arms the whole time, it's because they become so faint, so diffuse, that you have to have a really big camera, a really big telescope, and you have to be or you have to be patient. And this is one of those things where, and I don't particularly like the term amateur because it implies that people are just doing this that are not that good as a professional. This is a very different. They are for the love of the sport, so to speak. So people with their own telescope would be taking really long exposures, like I think 5 days or something like that, with their, we have a telescope like that. Is it still sitting outside there? Like these intermediate size, like something where you kind of go like, wow, that's a really serious professional, but or amateur. So somebody who's like really into the hobby and they buy like a small. For professional sizes, it's a small telescope, but for an amateur, it's like, yeah, you need a truck for that. Right? So they have these. They have their own little observatory in their backyard, for example, and they like this particular galaxy, and so they sit up on it. Right? They take a really long exposure. And so they collaborate with some people, with Martinez Delgado, and he has this catalog of what people have been able to take with 5 or 10 or 20 nights observing the same galaxy over and over and getting those really faint tails. And so we're seeing that evidence. Like you do see them, but you have to look really. They're much fainter than the night sky itself. The night sky is not fully dark. If you're here in Louisville, it's definitely not dark, right? You can sort of like it looks grayish because of all the lights. And if you go to a really, really dark site, you're in the middle of the Pacific Ocean, a Portal 4 site, or something like that. You can say like, yeah, it's really dark, but it's not fully dark. Okay, I need to get full moon. Okay, that was really, really dark, but it's still not 100% black, right? So that is still a light level, and often these little streamers are below that, so it's really tricky to get them. But it's really exciting that we're managing to find them because we're seeing the assembly bits for bigger galaxies, and we're seeing the tidal tails of collisions. Okay, so that's galaxies. I do the galaxy morphology. I do dusting galaxies. That is my area of study. I work with the Galaxies U folks, so they find overlapping galaxies for me, and then we go and find Hubble pictures or do follow-up observations, which is really fun. And so, yeah, this is what I do for a living, apart from this. So I do this, and I do research, and then a whole bunch of paperwork, but that's not interesting to talk about. Any questions about galaxies, please ask me anything. I know them, so. I can keep it on at length. This is why I cut everything down to a certain length. I'm like, you know what? I can keep going about bars. I can keep going about sizes of bulges. How many weird edge-on galaxies have a dust lane? Some of them do, some of them don't. That tells us something about the physics. So you can study galaxies as groups, as like whole ensembles, or you look at like individual things and go like, yeah, this is a real weirdo. But as a colleague of mine said, yeah, galaxies are only normal until you get to know them, like people. And so they're only normal looking until you look at them closely. Like they turn out to have like a collision in their history, or they have some other scar. And the other part is that, so we try to find something that is quickly transitioning. That green valley that you saw in color, that was, you're transitioning from blue star forming to red. And that must happen really quickly because there's sort of nothing in between. There's hardly any galaxies that are green. It's not easy being green. It's definitely the title of the paper that we've used, but it is a fast transition because you catch them barely ever. And it means that the star formation is dying off very, very fast. And so something shuts it off very effectively. And so we think AGN do it and mergers do it. But yeah, we work with
When you
undergrounds.
say fast, give us
Fast
a-
being, well under 500 billion years.
Half a-
Fast is a relative term.
Yeah.
So, yeah. But I worked with
500,000.
students, I had with undergrads, for example, and so one of my undergraduates using Galaxy Zoo, she found that if you have more spiral arms, you're actually relatively worse at making new stars. So more hands don't make lighter work. More arms don't help. I had another student who found in the Green Valley that lots of galaxies have rings, so something's up there with the rings. What was another? Oh yes, we looked at void galaxies, the ones that were really rare. They don't have bars, for example. They rarely seem to have a bar, so in order to have a bar, you need to have a neighbor or so. So maybe a neighbor just nudged you, and that's how you get a bar started, at least. So you can often tell something, but more as a general trend, rather than, I don't know exactly what happened to this individual galaxy, right? So it's very much like population studies, very much like, in general, if you eat fatty foods, you get heart disease, that kind of thing. That's true for most people, but then there's always that 120-year-old that goes, oh, I credit my old age to fat back and whiskey. And you kind of go like, how are you still alive? Or, not flammable. And so there's always exceptions to the rule, but trying to see the trends and also what the exceptions tell you. And so that's what I do for research. We're looking further and further back, so we're getting older and older pictures of, so from earlier in their development. And so we saw bars in the very early universe. There's one that we found 13.2 billion years ago. So there's a disk and it has a bar. So something managed to make one already. But other than that, they're pretty rare. most of the galaxies you see are little blobby things. And trying to find when the first black holes were formed, when the first stars were formed. We still haven't found those. That's why James Webb was launched. It is an $11 billion telescope. Now, $11 billion is a lot of money for all of us here. It's a lot of money for a space agency. It is a flagship observatory, right? $11 billion you spend once a decade as a space agency with normal funding. If you're in the US Navy, you go like, that's one of our 11 carriers without the air groups loaded up, right? They've ordered 11 of them, so you're gonna go like, yeah, their budget's a little bigger than ours. But it is a flagship, right? It is a big thing. And it taught us a whole bunch of new capabilities as NASA and as in combination with the Europeans and Canadians. And so capacities like this, actually developing something like that, takes a long time as well. The first time that anybody said, hey, let's build a big infrared telescope was 2000. It launched in 2021. It takes a while. It takes a while to design it, it takes a while to build it, it takes a while to get it right, and then you still have to mount the thing on a rocket, and it still has to have a launch window that works. So it became a like, gosh, when is this thing finally launching? That was 3 years of like, okay. So Christmas morning, James Webb launches, and in a reversal of how this usually goes, Dad dragged all his kids out of bed because it's like at 7 o'clock this thing is launching from Kourou, we're going to watch it. So we watched it and then opened present. It launched perfectly. This is an example of international collaboration where the rocket is European, French, and everything that was built on top was mostly American with European and Canadian contributions. So it is this kind of thing with like, yeah, if we all pool our resources, this goes much better. But it was a flagship, right? So the fact that it all went well would have been bad if it broke. I have an example of something that broke. The Hubble Space Telescope. Back in 1993 when it was launched, it was out of focus. So there's like 6 or 7 of you with glasses here, but we've all been to the optometrist, right? Right, where it goes like, better or worse, better or worse. Well, think of it as worse, 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 worse. And so it's like the pictures were blurrier than we took from the ground. This is not why we launched the Space Telescope. Again, took 15 years to launch. No, sorry, we had the telescope, it took 15 years to actually load up on a shuttle and get to space. Because this shuttle blew up in the middle of the whole program, so they had to wait for 3 years in order to make sure that it was safe. So these things take a long time. And the reason that I'm ranting about this is because, well, I want to talk about this at the end of the semester, but I'm happy to talk about this now. There is a big defunding happening at various science agencies. You don't notice that immediately, but if you're doing projects that have a 20-year timeline, if we defund it now, we're not going to have the flagship telescope in 2030, some mumble. Nobody's really totally clear, but it is the next decade. The next flagship is supposed to go up. It's something that you just have to keep at, and it's not something that you can just, pull the plug and, we'll just, throw some money at it. This is something you have to keep doing. Have a whole bunch of people just quietly work at it. You get the grand triumph of the launch at Christmas morning, and oh my God, was it fun on Christmas morning, but I know plenty of people who have been working on it for 15 years at that. We need people long term. And so this is something I want to talk about to you all, because I don't know how many of you follow the news, but this was one of the things that sort of slid under. A lot of funding, a lot of support for research has gone away. And research is people, and research are missions like this. So that's what I want to keep emphasizing. We get to do the cool stuff. We get to land a rover on Mars. That's another $10 billion project, but it is also a 20-year project, right? JPL did not think of a rover in 5 minutes, slapped it on a rocket, and went, right? It doesn't work that way. If you want to see how that works, well, you can see the little bits of Elon's latest rocket fall into the ocean. That's how that works. If you run, you can do this fast and break, what is it? Move fast and break things. NASA isn't about breaking things, it's about getting it there. Yeah, nobody sort of launches with their fingers crossed. That's not how NASA works, right? We check everything triple. And so that's what I wanted to sort of leave you with. I'm happy to have like a discussion on that, like with the class at the end of the semester, but I want you to keep that in mind. This is important, but it also includes the people, right? Infrastructure isn't just the rocket, isn't just the thing, it's the people who know how to make the thing. And it's not that many. So, I don't know, I didn't want to land on a bummer, but sorry I did. So I'll talk to you all on Tuesday. We'll talk about the whole universe as one giant physical system. And then the week after we do final prep. Right? It's exactly like we did.